Please present James Ward.
Awesome. Thank you. Thank you. Good morning. Welcome, everyone. This talk will be about the architectural patterns for distributed and decentralized data. And unfortunately, my co-presenter, Ryan Knight, who is the real expert on all this, couldn't make it to the conference due to a health issue, unfortunately, but he's okay. So get to do it by myself today. That'll be fun. I do want to do a little shameless plug about my podcast, Happy Path Programming with Bruce Eckel. The reason I point this out is because there are three great episodes that kind of take some of these ideas further. And so the episodes you want to listen to are one with Jonas Bonaire, one with Victor Klang, and one with Heather Miller. And so lots of good stuff in those episodes that'll go beyond this. Okay, so I want to try something a little different today. If you have a phone and want to participate in some way in this presentation, go to the slido.com and put in that code 118500 or scan the QR code. You can trust the QR code. You can trust me. This will, I'm going to try to get some participation, some back and forth with you all. I did a presentation on Monday, and I couldn't get anybody to ask any questions. I kept threatening them, if you don't ask questions, I'm going to show you Scala. And they didn't ask questions. I was so surprised. So I just kept showing Scala. So I'm not going to threaten you with Scala today, but I do want to hear a little bit from you. So here's the first question that if you go to Slido, you can participate in this little poll. Is the hardest thing about distributed systems is. And I think on this one you can like the hardest thing about distributed systems is a number. Yeah, that's true. Once you get in, you can put in some words. Testing, people. Oh yeah, people is always the hardest problem. Data sync, monitoring, transactions, learning curve, error tracing. Oh man, so much good stuff. See, this is fun. I like this. Consistency, transactions continues to be a big one there. State management. Yeah, good answers. Hey, that was kind of fun. So we'll do the stay on Slido. We're gonna keep doing more Slido stuff as we go to try to keep the interaction between me and you all going. I can't even really see you, but at least I can interact with you. Okay, so it came out a lot in your answers there that with distributed systems, one of the biggest challenges is data. Data is the hard part. And my friend Jonas Bonaire, who's presented here on the stage many times, he has this great quote where he says, "The heart of distributed system design is a requirement for consistent, performant, and reliable way of managing data." So yeah, it's the data is the hard part. The getting the data consistency, the performance, the reliability that we want, that's the hard part with the distributed data. But cloud was supposed to fix all this, right? Cloud was supposed to make our lives so much easier. When back in 2008, these are my servers. And I had a few servers in a data center in California, and it was fun having my own servers. And I'm sure many of you have managed your own servers at some point in your life. What's funny in this picture is you actually see an orange strap around some of those servers. They're actually holding the servers to the rack in the case of earthquakes. So in California, they get earthquakes. And for some reason, our servers wouldn't rack mount to the rack that was there. And so we literally just took this orange thing and strapped the servers down so that when they wouldn't bounce around during an earthquake. So that was fun times. I spent a lot of time praying to the gods of the data centers that nothing would happen to those servers, that they would stay up and running. And for the most part, they did. I think I only had a couple all-nighters in the data center fixing some Linux issue or something like that. So cloud was supposed to fix this, make my life so much easier. But here's some sad truths that I've had to realize with cloud, is that servers are unreliable in the cloud. I mean, my servers in that rack, they were certainly unreliable in some way too. But in the cloud, I think this goes even further, where in the cloud, our servers are constantly being recycled, turned off, turned back on again. We just can't depend on our servers always being around. It's not mainframes where the thing just is going to keep running for 100 years or whatever. So in the cloud, unfortunately, our servers are unreliable. But also, in the cloud, our networks are unreliable. So latency can change, networks can go down. A network engineer like me can make a bad configuration change and screw up the VPC. So not only are our servers unreliable, our networks can also be unreliable. And then the last one here is that our data centers are also unreliable. We've seen many outages that impact whole data centers from cloud providers. So unfortunately, the cloud doesn't necessarily make all of our problems with reliability go away. But what this means is that our data, it has to be distributed. And there's obviously many different reasons for this. One being reliability. We don't want to lose our data. Another just being scale. So we sometimes, we have to have our data distributed across the globe for regulatory reasons, for performance reasons, whatever. Okay, so let's go back to Slido and go on to the next question here, which is, if I can move to poll number 2, is my data, so this is asking you all, my data is on a single live server, maybe you got backups with data somewhere else, or is your data on multiple servers in a leader-follower setup? Is it on multiple servers with some other setup, or is it in the cloud? Meaning it's not my problem. I don't have to think about how my data is distributed. I don't have to deal with these challenges. So looks like kind of most people in the cloud. That's good. That's progress over the last few years. But still, some people on a single live server, some people on multiple servers in different configurations. So yeah, interesting to see how that all works. Thank you for answering that. Okay, now here's another follow-up to that question is, in the future, I need my data to be. Oh, really? Like people want their data to just continue to be on a single server. Interesting. I'd like to talk to you afterwards about that. Yeah, I think for a lot of people, we're moving to the cloud. We're trying to get to the place where we don't have to think about some of these problems anymore. We can hopefully use the cloud service, or we don't have to think about the reliability issues and the performance issues. But they don't all go away, and we just have to think about them a little bit differently, and that's what we're going to talk about. So, okay, thank you for answering those and engaging. That's pretty fun. Okay, so distributed data. We know that that's kind of generally, not all of us, but most of us need to get to distributed data. We need to get to the place where either the distribution of the data is somebody else's problem, or maybe it's our problem, but either way, we likely have to get to distributed data, but it's hard. So one of the reasons why it's hard is summarized in this quote by Andy Pavlo, which says, transactions are hard, distributed transactions are harder, and distributed transactions over the WAN are final boss hardness. I'm all for new databases, but people should tread carefully. So yes, there are some serious challenges to doing transactions, especially when we get into data that is replicated over long distances. Those long distances are part of the reason why distributed data is hard. Because, here's a little quiz, does anybody know how long it takes light to travel from Stockholm to Sydney? So, speed of light, how long does it take light to get from Stockholm to Sydney? Anybody? Shout it out. 40 milliseconds, pretty close. So, 50 milliseconds. 50 milliseconds. It turns out light is really slow. Distributed programming probably wouldn't be hard if we could just speed up light. That's the easy solution, right, to making this all easier. So 50 milliseconds is the minimum amount of time that it'll take light to get from Stockholm to Sydney, Australia. And of course, we're still going to have to go through some routers along the way. There's refraction has a cost. We're never going to actually get 50 milliseconds. But then usually we have to go both ways. You have to be able to communicate back and forth to do anything useful. So the minimum round trip from Stockholm to Sydney and back is 100 milliseconds. And that's pretty slow, actually. That has a big impact on how we deal with data synchronization. So that's one of the big challenges with dealing with distributed data, is just that the amount of time that it takes to cross the planet, to take your data, move it from one place to another, is actually pretty slow. So then there's some challenges around consistency. This is one of the things that was mentioned at the beginning in that poll, was that consistency continues to be a big challenge. So the traditional way that we think about doing transactions in ACID, it just doesn't scale, as you saw in that quote earlier. And so we also have some compounding problems. So when we deal with consistency at a global scale, if we have to synchronize data into 10 different locations around the globe, then we've just compounded the problem of data consistency. And we've taken that 100 milliseconds and potentially made it a lot more as we go to a microservices architecture. And if we've got, the latency can just add up and add up and add up. So it becomes a huge challenge for how we do data orchestration and microservices. And then we hopefully are thinking about things like, what do we do when the service fails? And if you've got your backup in some other location that's a long ways away from where you need to get the data, and you need to rehydrate a service, and you're rehydrating terabytes of data over a slow, high latency network, that could potentially take a long time. Maybe faster just to put the disks into a shipping container and ship it, So some crazy options there for rehydration. So what's happened in distributed data is that the global scale and the reliability that we need out of our systems, it has led us to, in a lot of ways, getting to what's called eventual consistency, where we say, all right, I don't care that my data is correct everywhere all at the same time. I'm going to just have some way for the data to eventually arrive at consistency. Okay, so now let's talk about eventual consistency in the real world. I love this comic. Hopefully you can read it. I'll read it to you because it is just so fantastic. So starting in the top left, there is a woman that says, "Oh, the kitty is stuck in a tree." And then she says to the person, "Do you think you can climb all the way up there?" And the superhero says, "No need." Reaches down below into the frame below and then gives her the kitty. And she says, "Kitty, thanks, invincible." And then down in the bottom left, she notices that there are two cats now, one in the tree still and one that she was handed. And she says, wait, what? And she says, "Wait, there's two." And the superhero says, "Yes, but no, it's just a little bit out of sync. Check again." And in the last frame, you notice that the cat in the tree is now gone, and she says, "Well, you're right." So yeah, just a wonderful picture of eventual consistency. This idea that, at some point, like, there's going to be, with eventual consistency, things will be inconsistent. And when will they be consistent? We're not really sure. Some point in the future, they will have consistency. So why does it matter that we have that eventual consistency may be a problem? So when we have eventual consistency in a system, there's places where that weak consistency can actually be a security concern. So it could be that that this weak consistency could actually cause some financial loss because we have lost data or come to not been able to resolve the data correctly at the right time. It could be that our data is based on actual things in the real world, like a flight, a seat on an airplane, a hotel room. There are actual resources where you really want to be sure that you're not allocating a real world resource more than once, because there's only one of them in the real world. There's only one seat that someone can fill on an airplane, and so you can't put two people in the same seat. So obviously there are places where this weak consistency can cause some issues. So I think a lot of this comes down to that correlation of, like, all right, if we have this like physical resource and we're trying to model that physical resource in the digital realm with bytes, then we can potentially get into an area where the two do not align. The bytes do not represent the physical resource and the allocation of it correctly. So that's some of the places where eventual consistency can bite us. And I like to call this the compute reality paradox. So data is easily copied, but real-world resources are finite. And so this is where we get into a lot of trouble with our eventual consistency models and where things get really challenging, especially when we talk about redundant data that's distributed. Okay, so let's take a minute and talk about data consistency and what that actually means, since it is a central piece to distributed systems. So in what's happened is when our data mostly just lived on a single server that was up forever, our mainframes, we didn't have to worry about data consistency because we only had one place where that data lived. But we've been in this evolution or maybe de-evolution of consistency where for the needs, complex needs growing, for the scale needs changing things, we've had to adopt other models of consistency, and primarily eventual consistency. And so this has been something that has risen as a way to do things with NoSQL databases especially, and they certainly solve a problem. Not saying that they don't, but I want to talk about the consistency trade-offs and the evolution of those. So you likely have heard of the CAP theorem and the trade-offs that you can make between consistency, availability, and partition tolerance. And it's definitely a useful model for thinking about the decisions that you have to make when you're choosing how to deal with distributed data. But it turns out consistency is a hard word. There's words that get overloaded and get reused and then kind of can lose their value and meaning. SOA was one of those for me. Anybody remember SOA? Like when we first started talking about service-oriented architectures, it's like we all kind of knew what we were talking about. And then at some point, the term SOA just got so overused and so marketed and that it no longer meant anything. And so with consistency, I want to try to bring some definition to the word so that we can hopefully not make consistency be where SOA is in terms of its value. Okay, so lots of ways to talk about consistency. The way that I'm talking about it here is not the same as we talk about it in terms of ACID. So ACID transactions, the C in there is consistency, and that is not the type of consistency that I'm talking about here. So what we're talking about is there's strong consistency and there is eventual consistency. Strong consistency is used to differentiate full consistency from weaker levels of consistency, such as casual or session consistency. So the consistency challenges that we have when we're dealing with data is things like dirty reads. So am I going to potentially be able to read a write that has not been committed? Am I going to get read skew? So I maybe read something once, but then if I try to read it again, it's not going to be the same thing that I would expect. Once I make a write to a system, can I read that write immediately after that? Is that going to always work? Is that going to be guaranteed? I don't know if any of you have experienced that exact phenomenon with large systems. I think one place where I experienced this once was I was like looking at Facebook on my phone and on my computer at the same time for some stupid reason. But I was doing this, and I was like VPN connected on my computer back through like the United States, but my phone was like on Facebook connected like through the internet in Europe, and I like posted something, and of course it like took a long time for that post to actually then show up onto my other computer. Like my two devices are in the same physical location, and yet they have totally different views of the data of Facebook. And due to the routing and the network, like obviously, like we can probably understand how it is actually happening is the data is being synchronized and just took a while to get all the way to the United States. So it's funny when you actually like see this in your normal experience of data. What's weird is we usually don't see this as often as we would think, which is, it shows us that eventual consistency in some cases can get us pretty far. And in the case of like social network, like who cares if it's eventually consistent? It's just like social network data. It's not, it doesn't relate to any physical resource. Okay, so can you read your own writes immediately after you write them? That's a consistency challenge. Do you potentially lose updates? So what if you are asynchronously sending updates and those just get lost? Something goes down along the way. Some packets get lost, and so that's something to think about with consistency challenges. And then write skew is also a problem. So write skew is defined as when two concurrent transactions each determine what they are writing based on reading a data set that overlaps with the other writing. So you get kind of like this circular dependency creates a write skew. So those are some challenges with consistency, and there's a great set of articles from Peter Baelis from Jepsen.io that breaks down these consistency models into a way and maps them to the CAP theorem. The CAP theorem, the way that CAP theorem talks about consistency is really just like this big bucket for consistency. So I like that if you really want to talk about consistency and break that down further into things that I think have more value and meaning, this content is really good. And I'll go through just a little bit of the consistency models that Peter comes up with to break this down further. So there is linearizability is a consistency model. And what this does is that it guarantees the order of the reads and writes to a single register or row will always appear the same on all nodes. So if we can do that, if we can get that guarantee, then we have linearizability. And this is about writes to a single object, and they should appear instantaneous. And then we guarantee that you can read your write. So with linearizability, you're guaranteed, because it's linearizable, you're guaranteed that if you do a write, that immediately after that, you can read that value. And then it doesn't group operations into transactions. So the CAP, usually when the CAP theorem talks about consistency, they're actually talking about linearizable consistency, not the next consistency model that we'll go into. So the CAP theorem is really just kind of focused on this linearizable consistency. Also could be called atomic consistency. So atomic consistency refers to a property of a single request-response operation sequence. So that's a narrow kind of perspective on consistency, and that all operations on a single object are guaranteed to follow a linearizable order. So there's this guarantee of ordering that is really necessary to have this linearizable consistency. Now, there's another model, which is serializable consistency. Serializable consistency gives us transaction isolation. It says that, all right, if the database can guarantee that two transactions have the same effect as if they were run serially, that's the serializable consistency. And this is allowing us to do multiple operations on multiple objects in any arbitrary total order. And so you can think of this as the isolation of ACID transactions. Okay, so that's our two consistency models, the high-level consistency models that we can look at things through. But if we take both of those, the linearizable consistency and the serializable consistency, and we put them together, then we get a new form of consistency called strict serializability. So it's both of those combined. And this is our highest level of consistency. If a system can give us both linearizable and serializable, this is the highest level of consistency that we can possibly get for data. And this requires guaranteed ordering and transaction isolation. So it turns out that if you evaluate the default mode of most databases that say that they're ACID compliant, they don't actually, when you look at them closely, they don't actually provide strict serializability. They provide a little bit weaker form of consistency. There are a number of them that have the ability to turn on strict serializability, and this is just in a single database. We're not even talking about distributed databases. So you can imagine if it's hard to get right for a just basic database, then it's really hard to get correct when you go to a distributed system. Okay, so those are our consistency models, linearizable and serializable consistency, and then together, strict serializability. Fantastic stuff from Peter if you want to dive further into those consistency models. I am a terrible artist, but I did try to draw what this looks like because, I don't know, pictures help me. Actually, writing pictures helps me, writing it down, even though it looks terrible. So with strict serializability, if I do a write to something, let's say I write foo to something, if the read starts after that write has started, I'm guaranteed with strict serializability that I'm going to read that foo out as long as that read started after the write started. So that's the strict serializability, is getting me that isolation and the linearizable, the order there. Non-strict serializability, if I do a write and that write takes longer than the read that may start after the write. With non-strict serializability, it could be that I read the previous value to that thing before the new value has been written. So that would be non-strict serializability. Okay, now here is the rub with consistency, is that there's not a single, like one consistency model fits all problems way that you can look at this. I love the Pat Allen quote where he says, do you want your data right or right now? And we have to choose. We can't have both. We can choose if we want it right or right now. And so there's another theorem that kind of takes CAP theorem a bit further. I'm not sure how, PAC-ELC theorem, but a quote from that is, in the absence of network partitions, the trade-off is between latency and consistency. So kind of similar to what Pat is saying, is that you can choose for things to take a while, potentially, or you can choose for that strict consistency, the strict serializable consistency. So we have to, when we think about consistency, think about what the trade-offs are to our consistency models and pick which one, where we want to be on that spectrum. And it is a spectrum. You know, you can be in that weak isolation level, you can be in that eventual consistency side of things, or you can be on the strong isolation level with serializable consistency. That's a spectrum, and you can pick where you want to be on that spectrum for every piece of data that you have. And this is hard. Like, I miss the old days when I just had a single server with a single database and didn't have to think about any of these problems. That was nice and simple and wonderful. Unfortunately, most of us don't get to live in that world anymore. And so we have to figure out for each piece of data where we want to be on the spectrum. So I think that generally, like, it's hard to say that there's a hard and fast rule for this, but generally we can break it down into two different worlds, where when something, as I was saying earlier, correlates to a physical resource that we can only allocate in the real world, then we usually need a strong consistency model for that. And if we're talking about money, then we probably need a very strong consistency model because the risks associated with screwing up the consistency are really high. Whereas on the eventual consistency side is things like analytics data, real-time analysis, monitoring, like Internet of Things, like sensor data. So I think generally this is a model that we can use to think about where we want to be on that consistency spectrum, is real world things that have high risk on the strong consistency side, and then the other side, eventual consistency. Okay. Let's go back to Slido, and I am curious on this next one. Which do you need more, strong consistency or eventual consistency? So for you all, which one do you need more with your data? And obviously, like, we need both in different situations, but just curious, which one is more necessary for you? Strong consistency seems to be winning, but yeah, I think that's pretty consistent with my experience and with data as well. Is that, let's say, about 60-70% of the time I need strong consistency, and maybe 30 or so % of the time I need eventual consistency. So awesome, thank you for that. Okay. So now let's talk about some of the architectural patterns that have emerged and are emerging to help us address some of this complexity around consistency and how we deal with data and the consistency challenges. So the first set of tools that we can use to deal with some of these consistency challenges are called CRDTs. And so CRDTs, they're called the abbreviation stands for conflict-free replicated data type. So it sounds kind of scientific and mathy, and it actually kind of is, because what CRDTs are all about is typically when you want to get to consistency, with like transactions as an example, you need a coordinator to make sure that your data is consistent. You need this like centralized coordinator. You need someone who is always in charge, who knows everything, and that coordinator can make the decisions to guarantee our consistency of our data. So that's kind of the traditional model of how we thought about, I need strong consistency. The only thing that I can use for that is this like centralized coordinator. Well, CRDTs are saying, no, you can actually get consistency in some places without the need for this centralized coordinator. So what CRDTs do is they define these data types that will guarantee convergence to the same value no matter what the latency is, no matter network partitions, message reordering. So it allows us to arrive to consistency without the need for that centralized coordinator, and this allows us to deal with not having guaranteed ordering, having partitions, dealing with latency, that sort of thing. So CRDTs are a bit of this like brain twist where we have to kind of rethink how we're thinking about our data. And a traditional database is so easy to think about. I've got this table, and I am just going to update a row in the table, and that's a pretty simple model. CRDTs, we have to kind of think about things a bit differently. Part of the challenge with CRDTs is that they get a little bit mathy because in order to have these guarantees, they base CRDTs on algebras. So the algebras are what gives us the guarantees and the ability to arrive to consistency because we're following algebraic laws. And algebraic laws are wonderful because they always work and always do the same thing. And so the algebraic laws are what drive the CRDTs to be able to arrive to that consistency without the need for the centralized coordinator. So this allows us to take data, replicate it across the network without having to have any synchronization mechanism. The synchronization mechanism would be a centralized coordinator, and we're trying to get away from those with CRDTs. So we're able to replicate data across the network and replicate it in a way with guarantees because of algebras. So we can avoid distributed locks, two-phase commits, those sorts of things. So we get the consistency without the consensus. Consensus is one way that we can get to consistency, but it's not the only way. So let's talk about what the CRDTs give us. Is it allows us we give up on the linearizability. So remember the linearizability consistency. We give that up. So that is not going to get us to strict consistency through the typical consistency model I talked about earlier. So we give up the linearizability, the guaranteed ordering, but we can still get to the correct answer. So this allows us to build if we look at CAP theorem, allows us to build the availability, high availability, and partition tolerant pieces, but not have the consistency of CAP, but still get to consensus. So there's a couple different CRDTs that have been discovered, and this is a very active area of research. And so what we're seeing is that there are CRDTs being discovered, and there are CRDTs that just people will realize, oh, in retrospect, this thing that we built actually is based on a CRDT, and now we have vocabulary and laws and algebraic laws to talk about these things, and this is all pretty recent developments for distributed systems. So one of the CRDTs is the monotonic sequence. So the monotonic sequence is a sequence that always increases or always decreases. And the monotonic sequence is eventually consistent without any need for a coordination protocol. So this is sending messages over a network, being able to monotonically increase or decrease something, a sequence, and have guarantees about the consistency of that thing. So an example of a monotonic sequence is Akka. Akka's cluster state, actually, they built this before the monotonic CRDT was discovered, but then later realized, oh, this is just the monotonic CRD. So the way that it works is in Akka cluster, the state, we've got like this ring of possible states. And the CRDT knows that the state goes from joining to up to leaving. And so what this allows us to do, because monotonic is only increasing or decreasing, the order of events is known. The possible order of events is known. So if a node sends a message and says, I am joining, and then it sends a message and says, I am up, the monotonic sequence knows that that is valid, because it can only go from joining to up. But once the cluster has been known to be in the up state, any messages that a node would send that say, I am joining, are discarded, because it knows that that sequence can only increase. It can only go around the circle one way. It can only go in one direction. So this ends up being a monotonic CRDT that powers how Akka keeps track of each node's state. So super cool. No need for the centralized coordinator to be able to coordinate the state of the nodes in the cluster. We just, in Akka cluster, use this monotonic CRDT. So there are different operations based on algebras and CRDTs. We can have an associative operation. You may remember these from math. That you can have a commutative operation, and you can have an idempotent operation. So associative allows the grouping. How we group things doesn't matter. Commutative means that the order doesn't matter. And idempotent means that duplication doesn't matter. So with these algebraic laws, we can build different CRDTs and assemble them into our programs. So some example operations here is I can do a union, and when I do a union, I can then know, all right, if these, it doesn't matter how many times I get a message A and a message B or a message C and what order they come into. If I want a CRDT that does a union, I can now have, it doesn't matter if I'm sending messages more than once, I can arrive to a union of data. Max values is an example of being able to, no matter how many times you get sent a particular value, if you're trying to get to a max value, then you can keep track of the state and, yeah, know the max. So you can disregard anything that is not a max one. Okay, another CRDT is a CRDT counter. So CRDT counters are grow-only counters. They only support increments. You can do a positive-negative counter. So you can have one going in one direction and one going in the other direction, one for increments, one for decrements. There's CRDT registers. So with CRDT registers, the last write wins. Cassandra columns are based on CRDT registers, and then also objects in React are based on CRDT registers. CRDT sets, they do a union, a merge, and it's a grow-only set in a CRDT set. You can also do an OR set, which uses the vector and birth dots, which I don't understand those pieces. So another CRDT that gets used in distributed systems to arrive to consistency without the need for a centralized coordinator is the whole point. Okay. Lots of exciting stuff happening in CRDT land. Definitely one of the most interesting parts around distributed systems and research happening there. So let's go on to the next technique that we can use to deal with distributed systems is CQRS and event sourcing. And so to talk about CQRS, I'm going to set up a little bit of background. And my experience with CQRS is mostly based on Kafka. So that's the world that I kind of see a lot of this stuff through. And so I want to just give a little bit of an overview of how I would do CQRS given a Kafka-like structure. So with typical CQRS systems, we have an event log. And you can think of this like a ledger, like an old accounting ledger, where we can only append things into the log. We can't ever go modify something. There is append only. And we have this ledger, so we can always go back at any time to the beginning of the ledger and replay through. You can start at any point in the ledger and play through. So if we have this event-only log, we can record these events sequentially in our system. And then one of the things that it enables us to do is to do a pub/sub-like system where our writes are disconnected from our reads such that we're always writing to the front, and then our consumers can be connected and listening and start at any point they want in the log. And so this allows consumers to be running at different speeds, running at different points in time through the log, and you can attach consumers that can choose where they want to start and what they want to do at any point. So some cool things that we can do when we get this append-only log. And in the case of Kafka, there's some different guarantees that we get on the producer side and the consumer side. So on the producer side, you can choose when you produce a message to fire and forget, which is just no guarantee of consistency. You can say, I want to be, before you confirm that you have received this message, I want to make sure that that message has been committed to the leader node. Or you can say, I want to ensure that it's been committed to the leader and the quorum of followers. So that's on the producer side, the different guarantees you can choose. Then on the consumer side, you can choose different guarantees around how you want to consume the data. The default with Kafka is at least once. So this means you're guaranteed that when a consumer connects, it's going to get a piece of data at least once, but could get it more than once. There's also another mode called at most once. And then there's a great term that Victor Klang, I'm pretty sure, coined called effectively once. And effectively once is at least once delivery with idempotent operations based on that. So if you can have idempotent operations and you do at least once, then you get effectively once. And so that a lot of times everyone kind of wants exactly once. Exactly once is the dream. And we can listen to my podcast or talk to Victor or Jonas about how exactly once, it really isn't technically possible. Like, it's really, really hard to get exactly once delivery in a distributed computing, in a distributed system. Okay, so let's just imagine that for most real cases, exactly once isn't a possibility. So effectively once is often a good way to do that instead. Okay, so those are our delivery guarantees. Now, the way that CQRS works is and I don't know if I said it, it's command query responsibility segregation. So in CQRS, we have commands. So we're going to send a command and store that into the log. And a command could be something like add transaction, and we put in the information about the user and the kind of transaction and the amount and the date. And so we store that in the log. And then we can because our log is just all the events that have been recorded, we may want to do a query. So an example query would be, what's my account balance? That seems like a very good question to be able to ask to your system. How do you do that when all that you have recorded is the log entries? Well, what you can do is you can replay all of the commands. So we assume that our default balance our starting balance is 0, and then if we play a transaction for that user that is an add transaction with an amount, and then now we know their account balance is $31.27, and if we get another add transaction that adds $5, then we know that it's now $36.27. So with CQRS, you can replay the events that have happened to be able to arrive to the state that you would normally store in a database table. So with CQRS, we have to have ordered events. So it requires a consistency model where we get that linearizability. And what we do is we usually in CQRS create what are called materialized views. So materialized views allow us to take a view of the events being played and be able to have a view that represents some computation on all the events. And so that is how you can keep the users balanced, so that when they go to the web page and want to know their balance, you can just pull that out of the materialized view. But the important point is that the log is the truth. In a CQRS system, the log has to be the truth, but you can materialize views that are just computations on the logs that are there. Now you may be thinking, oh gosh, this sounds like a terribly expensive thing to do, to have to be able to go through all the events in the whole history of all events ever to be able to get to a view. And so what most CQRS systems have is snapshots, which allow us to take snapshots at given points in time as we're playing through the log, so that if we do need to recreate a materialized view, we don't necessarily have to go all the way back to the beginning of time to do that. We can start with a snapshot and then replay from that snapshot. Okay, so that's CQRS, but big important thing is that the log is the truth, which requires linearizability. And then again, you have to think about, in the case of Kafka, what are the delivery guarantees that you need to put into place on your producers and on your consumers, given the data. You can be much more on the eventual consistency side, or you can be much more on the strong consistency side, depending on what your data is and what you need. And you have to make that decision when you are building your system. Okay, now the last kind of pattern I want to talk about in distributed systems is the Saga pattern. So with the Saga pattern, we are trying to get to consistency. So that's the big problem that we're trying to deal with here, is get to consistency. And now that if we're trying to do transactions across a distributed system, one way that has been used to do this is the Saga pattern. So what it's doing is it's moving that checking, that verification of consistency out of the database tier and into the application tier. So there's some nice things about this. We get low read and write latency, and we can get high throughput. If you're in the same session, then you can be guaranteed that you can read your writes. And so there's some challenges. You have to make sure that a given session is sticky through a given server, so that because underneath the covers, the data is becoming consistent later. And so you have to make sure that the application tier is providing that consistency. But it turns out that there's some disadvantages to application tier consistency in the Saga pattern. Some of those being that the consistency is actually a really hard problem to solve in the application tier. So you're increasing the complexity. There's no isolation. You now have to have this centralized coordinator to coordinate this, the consistency of the system, and it just ends up being. There can be a lot of bugs that come up where your consistency model, the thing that is applying your consistency model in the application tier, may not be doing it correctly. And so that can mean that you are getting inconsistent data. So requires the centralized coordinator. That coordinator is managing the transaction logic. And you are in the Saga pattern splitting the work into item executors and requests. So the Saga pattern, it's been used, but the challenges with it continue to kind of bring their head up, and in weird ways too. It turns out like rollbacks can be really hard with the Saga pattern. With the Saga pattern, you need to be able to have item potency, and you can't always make everything item potent, unfortunately. So a good example of something that is not item potent is sending an email. Once you send that email, you probably don't want to send it again because your users are going to be annoyed, and you can't roll back that sending of the email. So there are places where you just can't do item potency, and so I Ryan, my co-presenter, he can go on and on about the distributed systems that he has had to rip out the Saga pattern on because it didn't do a good job providing the consistency that was actually needed, and just caused a lot of issues. So this was Ryan's way to view the Saga pattern. It's just, it feels good at first. Everything feels right, and then it just throws trash all over the distributed system. So yeah, that's, I would say don't use the Saga pattern. Okay, event partitions, real quickly, go through these. So with an event partition, this is based on the way that Kafka does it. We can partition our data. What this means is that we no longer have a global sequential ordering of events. We have partition ordering of events. So this allows us to horizontally scale both our producers and our consumers across a cluster of machines. And so just a way to get some of that with the consistency, also get some of the high availability and scalability that we usually need. So, okay, I'm going to just end with one last little Slido, which is which pattern. So you've seen some different patterns here for distributed systems and dealing with things. Which are most useful to you? Saga pattern. Good. Well, hopefully the Saga pattern continues to work well for you. But CQRS, yeah. CQRS, I should mention, I've done CQRS also with Flink and had great experiences with Flink for doing CQRS stuff. So lots of good stuff there. Yeah, event partitions, good. Okay, well, I'm glad Saga had an early lead, but yeah, down to 10%. So, okay, well, hopefully that was useful for you all, and I'll be around if you have any questions. And I think that, oh, I didn't want to mention, I don't know if Jonas is here. He was supposed to be here to talk about Akka serverless, but real quick, CQRS is pretty hard to do. The developer experience is not awesome of CQRS. It's challenging to get right. Akka serverless is doing a really great job to make CQRS and CRDTs a lot easier. So if you're interested in kind of the easiest path you can find for doing CRDTs and CQRS, check out Akka serverless. They're doing a lot of good stuff there. So, all right, that's it. I'll be around if you have any other questions. Thanks so much for coming. Thank you.